Good morning, everyone. We're about to start the session. This session here, just to be clear, is going to be the Advanced NLP session. If you're looking for the computer vision one, is upstairs in room B12. But yeah, so opening the session is Oriol Vinyals. Oriol is a senior staff research scientist at Google DeepMind, working in deep learning and artificial intelligence. Before joining DeepMind, Oriol was part of the Google Brain team. His research has been featured multiple times at the New York Times, BBC, etc., and his articles have been cited over 30,000 times. Some of his contributions are used in Google Translate, text-to-speech, and speech recognition, serving billions of queries every day, and he was the lead researcher at the AlphaStar project, creating an agent that defeated a top professional at the game of StarCraft.
Hola. Gracias. All right, yeah, it's working. Buenos dias, bon dia. It's a pleasure to be here so early, but Khipu has been so far amazing for me, and I've been here just actually over a day. Sadly, I couldn't come earlier. So today's we have a parallel session. This is the NLP one, and I'll start with something that's probably not very advanced NLP, but then later in the session we'll see some trends and things that have happened in the past year or two, and also some very interesting applications of NLP, which I'm quite excited to learn about myself, actually. I'm not aware of these work, so that's how advanced it is. It's super, new. So let me start with just, as I was saying, I'm going to talk a bit about almost like a historical kind of trajectory of things that we've seen in deep learning in particular and NLP, because it's quite important sometimes to understand where we're coming from. When we see a new paper, oftentimes we don't understand why did this happen now and so on. So I'm going to try to explain more like sequence of events and why things happen in research hopefully. So let's actually travel back in ancient times. So 2014, those doing deep learning research found it quite challenging, actually, to think about modalities that were sequential in nature and had this variable length nature that language and sequence data have, right? So we knew quite well how to treat fixed dimensional inputs or vectors, like images or features that you might construct from your task. But it was quite annoying to think about how do we encode this variable length stream of observations that, of course, we need to deal with in natural language processing and related things. And obviously, that was sad because sequences do appear a lot in problems that we might care about solving, such as, of course, words, letters, but also speech, sequential decision processes, programs, videos, and so on and so forth, right? So for deep learning, it was important to make sure we can actually uncover the capabilities necessary for us to deal with this. So this is a bit like very basic, but to give you a bit of intuitions of, okay, what was needed and what are the ingredients, so to speak, so that we can encode these variable length sequences. So here in this example, we have just a short snippet of text. The cat sat on the, and it obviously will continue, probably if it's proper English. And we want to have a function f that will take this and convert it to a vector or an embedding. And this has to satisfy certain properties. Obviously, order in language at least matters. So if we just add the word embeddings, that would be pretty naive to do and pretty bad. Matrix multiplication, so taking this and putting it into a normal deep neural network wouldn't be so great, because then we wouldn't be able to extend this sequence beyond the maximum number of tokens that this matrix can take. We also want this f function to be flexible and learnable and ideally differentiable, so we can just train it on any loss that we might care about, and Jorge is going to tell us about losses later. And also, it needs to be powerful, right? When we change a word, we know the meaning can change quite drastically. So this ideally should be a very powerful deep neural network. And then, of course, last but not least, some words connect far in the sequence, right? A word I'm saying now might have an impact in many, many sentences that I will say in a few minutes. So it is important that this function preserves long-term information. So what happened back in the day, and Cho also, of course, discussed this in his lecture in detail, is that we propose sort of a recurrent neural net architecture that had some properties of long-term capabilities, either LSTMs or GRUs. And also, we started to be quite creative in how could we not only decode a sequence of observations, but also input sequences of observations in the models and so on and so forth. So this was kind of published in the same year, actually in 2014, called Encoder Decoder or Sequence to Sequence. And the idea was very, very nice in terms of simplicity. Simplicity is always nice in terms of research because it means probably it will be adopted more easily. And the principle here was super simple. We take a sequence as an input, we put it into some LSTM memory that builds upon knowledge of this sequence, and then we start decoding perhaps a target sequence, which could be, let's say, a translation. That's what was the motivation for us to work on this. And then you start decoding sort of the Spanish to English translation, for example. And Karpati put this quite beautifully. He kind of explained that thanks to these recurrent neural networks, LSTMs, and so on, you could really think of now many applications that were suddenly unlocked, where you could map all sorts of sequences or input modalities to a sequence, and so sequences can be now inputs, outputs, and the field, the community really thrived on this. We really started seeing an explosion of applications of sequences now using deep learning or these recurrent neural nets models, and that was kind of the times of discovery of, okay, now that we have the capability of dealing with sequences, what can we do about that? So of course, it's difficult not to tie this to machine translation, where now it's used pretty much everywhere to translate languages. This is not obviously a solved problem. We know there's problems still in machine translation, but just the fact that it's end-to-end and so on and so forth, it's quite impressive compared to the state of machine translation before 2014. One of favorite applications here that might relate later with the multimodal NLP track is captioning. So the very first thing that we did actually at Google Brain after translation was this funky idea of translating an image to the caption. And the cool thing here is that I literally took the same code, changed one line, encoded the input sequence, which was an image with a pre-trained inception model, and I came back the next day and I started seeing really captions that looked like it was doing a reasonable job at captioning an image rather than just saying which label this image is part of, right? So this is open source, and there's a lot of course, follow-up work on these ideas. And one maybe aside that I want to say, very importantly in deep learning, and if you've trained models, you know this very well, but it must be said like openly, is that many times the ideas and the models sound reasonable, but tuning these models and hyperparameters is super important. So one thing that we did back in the day, we published a paper at CVPR, and we had captions such as the ones at the bottom there. So this one is, would say, a close-up of a person eating a hot dog, which you could kind of see if the hot dog was yellow, but clearly this is a maybe more humorous caption, but not really good. But then just tuning the same architecture, I didn't change anything, just tuning the size of the network and the gradient update, the clipping, all these tricks actually made it much better to the best model that then we submitted to a competition that has been ongoing, that Microsoft organized. Now, language also comes in different modalities. So one very interesting project was WaveNet, in which we actually use the same principle to map a sequence of characters or phonemes to the actual sounds. And here, what was probably beyond what I actually expected to work is that we don't generate like maybe Fourier transform bases that then we decode into audio or anything like that, or like most people were doing, which is kind of copy-pasting small pieces of speech. We actually generated speech as if it was literally a language, right? So it's a long sequence of numbers or integers, and we treated that as if it was language, and it actually sounded really, really natural, right? So this actually is what is now currently driving Android voice, for example. So it's very interesting to see how the same ideas kind of translated to many modalities as well that relate to language and sequences in general. So there are many, many more applications, but now historically we were at this excellent moment where sequence-to-sequence was really delivering, but there was also a bothering problem that is, if you look at this model, you encode your input sequence A, B, C, D, and you keep kind of trying to compress all this information into that little box that represents a recurrent neural net. So this creates a lot of pressure to compactify all this information onto that box, and this just feels wrong, right? Like that you take any length sequence and it can be sort of integrated into a state one step at a time. I mean, it's very cool on the one hand, but it feels like there's something better that maybe we can do. And that's when sort of the ideas related to attention came about. So let me explain a bit the intuition here. The intuition is that as we decode, we would like to read at each time step of the decoder, we would like to read or take a look at just the whole sequence, which is very natural. If you're translating some text, you will not just read the text and close your eyes and then start writing the answer. You will kind of go back to the original sentence in Spanish or paragraph, and you will try to kind of go back and forth. And this iterative process is a bit here neuralified, if you will, through this idea, very basic idea of attention, which I think was one of the key results probably in the last 5 years in deep learning and neural networks. Now, there's a caveat here that if you think of attending over this input sequence, let's say I have this sentence, I am a cat, so it has 4 symbols, let's say. You could imagine, well, I'm going to do an attention mechanism by doing a softmax over 4 outputs, right? So you take your decoded state D, that might be a 256-dimensional vector. You apply a matrix multiplication, so that gets mapped to 4 numbers. These 4 numbers represent how much I want to attend to these 4 input words. And that's how you create this readout, if you will, from the input. Now, this is not great, because if I added any word here, for instance, now I say I'm a grumpy cat, this softmax matrix has 256 times 4, but now your input sequence has 5 elements. So how are you going to attend over this, again, variable set of inputs? And we were attempting to do these sorts of things prior to 2014. But really, what solved it was this brilliant paper from Badenau et al., which said, don't do a matrix multiply over a 256-dimensional vector. Do a dot product between the 256-dimensional vector D and then all the input embeddings E. And every of these dot products creates a number. That's how much you want to read from this input element. And if there are more numbers, more inputs or E's, then you naturally create another product, you have another number, and you have a softmax over a variable or dynamic element set. And now we have happy cats instead of grumpy cats, which is great. And I had to add this slide because Mayre really likes cats, so kudos for her. So this, again, created sort of an additional set of things we could do that maybe sequence-to-sequence was not allowing us to do. I love this example where you do captioning, but you see the attention over the image where it lies on, and you can see how some words relate to the objects that you're kind of outputting one word at a time. And then another application was lip reading, which is kind of a very challenging task for humans to do, actually. And attention was done over the audio and the video to then decode words, which actually I thought this was kind of unbelievable, right? So you get word error rates from professionally 70%. It's really hard to do lip reading properly. And then the neural net was able to go to 50, which is still very high word error rate, but of course, a bit better. And as a last aside of what happened with attention is this idea that you can take these dot products to read out from the input sequence, but you can also take the dot products and say that distribution over the inputs, that is how much I want to read from each of the inputs, might be useful in itself, actually. So at 11, I'll talk a bit more about this because it was a key element for the agent that plays StarCraft. But here, the idea is just use the attention to point at elements of the input so that you can start doing things like trying to input a set of points and output some geometric properties for this. So this is the convex hull, and we also played with these ideas of trying to solve NP-hard problems with neural nets. So I recommend you go to look at many papers that appear. But actually in language, this also had played quite a key role, which is in summarization, right? So when you read some very long piece of text, there's a way to do summarization, which is just to reuse the words that appear in the long text to summarize it to short. And to do that, you must have a way to point to words in the original text to start outputting them one at a time. And there's brilliant work. I really like this one from Abigail. So she had this idea that you could summarize, and the letters are really too small, but here, if there's someone from Argentina, they might not be happy because they talk about Germany beating Argentina. But anyways, jokes aside, these pointer nets have also found many applications in NLP. So let's look at the last bit before Jorge tells us a bit about BERT and friends. So there's a desirable property of F which maybe we as a community missed when we were building upon these attention models, which is the capability for a word to affect another word very far away in the sequence, which is quite important because, as I said, long-term correlations do exist in text generation. So this idea of powerful pairwise encoding is precisely the key component that appears in transformers. But before I just tell you what transformers are in one slide, I'll tell you that transformers are of a family of models that deal not with sequences, but with graphs, which I'm quite excited about, actually. And I saw some very good posters using graph neural networks. So the idea here is, let's treat a sequence of words not really as a sequential data, but more as a cloud of information or nodes. So each word here would be represented as a node. And then you can use a graph that connects maybe all words to all, or maybe a subset of words to a subset of words. And then there is nowadays also capabilities for deep learning to be able to deal with this new modality beyond sequences to graphs, which is very cool. But actually, self-attention, or the idea behind transformer, is quite similar to interpreting all the words as a fully connected graph, but perhaps another way to see it is that it's a bit of like thinking of you do a convolutional neural network in which you have this fixed set of weights that you combine on the 1D structure of text. So that would look like so, right? So this on the left is a fixed set of weights that you learn with gradient descent, but once they are learned, you pass through the text, and that's how you would then create the embedding of the next layer. And what's cool about self-attention is that it's a convolution over all the input sequences, and it uses the idea of attention, this idea of dot products, quite extensively to make the weights or the strength of these connections depend on the context or the input word. And this insight is actually key and has become essentially a building block now in deep learning, maybe the latest one, that's really changed not only NLP, but also generative models, vision, and so on and so forth. So this is a cool animation of transformer, but of course you can see that in the open source libraries, or the multiple of them, because this has become actually quite a popular paper that was written in 2017. And in terms of desirable properties, transformer has this idea of pairwise encoding, where every word can be encoded in conjunction with any other word in the sequence, which actually is quite important and useful. So the last bit before I let Jorge speak about BERT is actually this very cool paper from our friends at OpenAI that is called GPT-2. And so here, what's beautiful about this is its simplicity. So there's a very simple formula where they took lots of data. They took actually 8 million websites and scraped the text out of it. A very deep, big transformer with 1.5 billion parameters, which is a lot of weights to be tuned with gradient descent, lots of TPUs, and that's it. They train a language model on all this data. And a few things happened. One of them was that the samples we get from these models were quite remarkable. So this is a bit of a historical perspective on generative models of language. Crucially, what I like a lot is that actually Shannon already kind of explained how you would sample from an n-gram language model back in the 50s. And these models, if you look at samples at the top, they look kind of incoherent, right? Each word is kind of okay, $6 billion. But then you look a bit further, and it just talks about, it's kind of nonsensical, right? And then RNN language models really improve the sample quality. And so through years, you see things like short sentences that start to almost look like they could be written by humans. I really like this paper that proposed a transformer for the first time that generate whole Wikipedia articles. So you would condition it on wing over Kansas, and then you would see text that keeps talking about wings over Kansas. And I think here is like, it's a film, so it keeps saying, oh, this film is great, and so on and so forth, right? But then the sample that they showed for GPT-2 was probably beyond what we thought was possible in terms of coherence and text generation goes. So very appropriately, actually, they chose to prime the model with a sentence about the Andes, which obviously we know where we are, and so that's quite nice. And then you have this priming like, oh, in a shocking finding, scientists discovered unicorns in the Andes, and then it goes about like saying, then it starts generating, right? So it says the scientists named the population after this distinctive corn, and it talks about after 2 centuries. The mystery of what sparked this odd phenomenon is finally solved. And this is not made up, I promise. But the next sentence, Dr. Jorge Pérez, who is here with us, actually, and he's going to tell us all about this evolution of this unicorn. So I'm really looking forward to the next talk. But you can kind of see that things make sense in this language model. And it keeps going on and on with some nonsensical things, but mostly coherent long-term text. And of course, what to me was super cool, very originally, is that once you have this model that can generate these samples, you can also, in a smart way, prime it to do neural language model tasks or new NLP tasks almost for free, right? What we call zero-shot transfer. The idea is very simple. You can use priming, so you can put a long text of English, and then you say TLDR at the end, which is what people would kind of talk when say, well, this is very long, TLDR, this is the summary. And this language model was able to perform summarization just by adding this TLDR word at the end of a long sequence of text that you would pass it to the inputs. And similarly, you could also prime it to translate from English to French. So you would say an English sentence equal to the French. So you give it that as an input. And then you want to translate a different sentence, and you put English sentence number 2. You put an equal sign, and then you generate the answer, which happens to somewhat be the translation. So it's really remarkable how large-scale language models have been able to perform this zero-shot transfer task. So with that, I hope I gave you a bit of intuitions behind all these building blocks of deep learning that we keep adding capabilities as a community to deal with graph sequences and so on. And I think we have a couple maybe time for 1 or 2 questions, but we also have the panel at the end. Otherwise, thank you so much.